So we're going to finish 5.2 today. So we talked a little bit about this on example 1, but if we have two independent events, like we roll a dice and we roll a dice, or we roll a dice and then we flip a coin, if two events are independent, then the probability that two things happen are simply the probability of the first times the probability of the second. And in statistics notation, we say this: the probability of A and B is simply the probability of A times the probability of B. And that's only true when the events are independent. Okay? So, let's say I roll a dice and I flip a coin. What is the probability that I get 6 and tails? So first, are the dice and the coin independent? Yes. Okay? So we need to find the probability of the first one and multiply it by the probability of the second one. What is the probability of getting a 6? 1/6. So the probability of 6 and tails is simply the probability of a 6 times the probability of tails. Okay? So what is the probability of a 6? Yep, 1/6 times what's the probability of a tails? 1/2. And I end up with 1 times 1 is 1, and 6 times 2 is 12. So we have a 1 in 12 chance of that happening. Okay? Now, the other way to do it is to write them out. So I could get 1 and H, 2 and H, 3 and H, 4 and H, 5 and H, and 6 and H. What else could happen? 1 and tails, 2 and tails, 3 and tails, 4 and tails, 5 and tails, and 6 and tails. So how many of those allow me to win? Just one, this one. And how many are there total? 12. So the probability of getting 6t is 1 in 12. So this probability of A times probability of B is just a shortcut. You don't need to write everything down. Okay? So, what is if I roll 3 dice, what is the probability of getting 4, 1, 2? Well, does the first dice influence the second dice or the third dice? No. So, they're independent, so we can multiply. What is the probability of getting a 4? 1 in 6. What's the probability of getting a 1? 1 in 6. And a 2? 1 in 6. So 1 times 1 times 1 is 1. And 6 times 6 times 6 is 216. So we have a 1 in 216 chance of getting that probability. Okay? Look at example 2. A group of 4 students includes 1 boy and 3 girls. The teacher randomly selects one of the students to be the speaker and a different student to be the recorder. Use a sample space to determine whether they're independent or dependent. So we have 1 boy and 3 girls. Is choosing the first person independent or dependent of choosing the second? Dependent, because the same person can't be in both places. Okay, so we can't use the multiply rule here. Okay, So the solution, let B represent the boy, and G1, G2, and G3 represent the girls. Use a table to list the outcomes in the sample space. So we either get B, G1, B, G2, or wait, we're doing just, yeah, that's right. B, G3. That's one way to do it. Or G1B, G1, G2, and then G1, G3. What's another way to do it? G2, B, G2, G1, and G2, G3. Have I covered everybody? Nope. I need to start with G3. So G3, B, G3, G1, G3, G2. So how many ways are there to pick the first two people? So we have 3 rows of 4, which is 12. And it wants to know what's the chance of randomly selecting a girl and then randomly selecting a girl? How many of those are girl-girl? So none of these count, and none of these count. We end up with 6 out of 12. Why did we not just multiply? They were dependent. When we have dependence, we can't multiply. It doesn't work that way. Okay? All right, example 3. As part of a board game, you need to spin the spinner, which is divided into equal parts. Find the probability that you get a 5 on the first spin and a number greater than 3 on your second spin. Are the spins independent or dependent? Independent. So we can multiply. What's the chance of getting a 5 on the first spin? 1 in 8. What is the chance of getting a number bigger than 3 on the second spin? There are 5 of those. 5/8. So the answer is 1 times 5 is 5, and 8 times 8 is 64. So 5 out of 64 is the solution. Okay? Example 4. A bag contains 20 $1 bills and 5 $100 bills. You randomly draw a bill from the bag, set it aside, and then randomly draw another bill from the bag. Find the probabilities that both A and B happen. Independent or dependent? Dependent. So I can't multiply, I need to write them out. So we have 20 $1 bills, and we have 5 $100 bills. Okay. So how are we going to set this up? Well, what could happen? So we could draw one $1 bill. We could draw the $1 bill with, we'll call all of the $1 bills 1 through 20, and then all of the, maybe we should do like A's and B's. So we'll call these A's, and we'll call those B's. That might help. So we could get A1, A2, and then A1, A3, and then A1, A4, all the way up to A20. A1, A20. Wow, I messed that up. Sorry, guys. Let's do that again. So A1, A2, A1, A3, A1, A4, A1, A20. Then what? What else could happen? Have I finished all the A1s? Well, I need to do A1, B1. So A1, B1, all the way up to A1, B5, and the smartboard just died. Shoot. Sorry. Now I have to rewrite that. All right. So A1, A2, A1, all the way up to A1, A20, and then A1, B1, all the way up to A1, B5. Okay. How many numbers are there in this group? Careful. 19. Because A1 is matched with everything 2 through 20, right? So there are 19 A1s with an A. How many A1Bs are there? So we have A1, B1, A1, B2, B3, B4, and B5. So there are 19 of these, and then there are 5 of those for a total of 24. So every row is going to have 24. How many rows are there? 25. How come? We have 20 A's and 5 B's. So this is going to be a box of information that's 24 across and 25 high. So 24 times 25 gives us a total of 600 items. Okay, so the sample space is 600 numbers big, and it wants to know so what is the chance that the first bill is 100 and the second bill is also 100? So how many BBs are there going to be? Well, how many rows start with B1? How many rows have B1 in the first place? How many of these rows here have B1 in the first place? So A1 only is in the first place for one row, right? So B1 is just one of these rows, right? Okay. What about starting with B2? There's one row. So we actually have 5 rows that start with B. Okay. Inside each one of those rows, how many of them also have a B? So we would get B1, B2, B1, B3, B1, B4, and B1, B5. So 1, 2, 3, 4. So there are 4 ways to do B1 with a B after it. Okay, so that's 4. And then how many times do we do that? 5 for every B. Now that's 20. So 20 divided by 600 should be our answer. And I end up with 3.3%. Now, that was way hard, right? There's got to be an easier way. Okay. So go back to page 289. Right in the middle of the page, it says core concepts. If 2 events, A and B, are dependent, then the probability that both events occur is the product of the probability of the first event and the conditional probability of the second event given the first event. So there's a little bit of notation you need to learn. Probability of A and B. Well, if they are independent, then we just do P of A times the P of B. That's easy. But if they're dependent, okay, if we have dependence, then it's the probability of A times the probability of B given A. So that right there says given. Okay. So we'll go back to that number 2. Example 2, we had 1 boy and 3 girls, and the choosing was dependent. Okay? So all we have to do is find the probability of A. So we wanted to know what is the probability of getting a girl first. So we're going to choose 2 people. What's the probability that the first person is a girl? We have 1 boy and 3 girls. Three-fourths, right? So this is 3 over 4. Now, 1 girl is gone. What's the probability that the next person is a girl? 2/3, right? Because now we're missing somebody. So 3/4 times 2/3, and we end up with 6 over 12, which is 1/2. So if your if your situation is dependent, then your second multiplication is going to change the denominator, which is way easier than adding them all up, especially when there are 600 items. Okay, so go turn the page. Go back to example 4. Example 4 is dependent. So what is the chance that the first bill chosen is a $100 bill? 5 out of 25. Does everybody get that? There are 25 bills, 21s, 5 100s. The chance that the first one is a 100 is 5 out of 25. Does that simplify? 5 out of 25 simplifies to be 1/5. Okay? And now the second bill is also 100. Well, how many $100 bills are left? 4. And how many bills are left total? 24. So we're going to multiply that by 4 over 24. Does that simplify? 1/6. And I get 1 over 30, which happens to be 0.03 repeating. Yeah, that is so much easier. So all you have to figure out is this idea independent or is it dependent? If it's independent, then it will be 2/5 times 2/5 times 2/5, because the second one is not influenced by the first one. If they're dependent, then you just subtract what you've already taken and then multiply what's left. Okay? Okay, example 5. You randomly select 3 cards from a standard deck of 52 cards. What is the probability that all 3 cards will be hearts? And A, you replace each card before selecting the next. So we're going to play this game twice. The first time, we're going to draw, look at it, put it back. Draw, look at it, put it back, and then draw and look at it. What is the probability that the first card is a heart? How many hearts are in the deck? Ace, through king is 13. So there are 13 hearts and 52 cards. What is the chance that this first card is a heart? 13 out of 52. Now, 13 out of 52 simplifies down to 1/4. Why does that make sense? 1/4 of the deck, 4 different suits. So there are 4 different suits in the deck and they all have the same number, right? So 13 out of 52. For that second draw, is it independent or dependent? If I put it back in, does that make it independent or dependent? Independent. So for this second one, what's the chance that it's a heart? The same, 13 out of 52, which is actually just 1/4. What about the next one? It's going to be 1/4 and 1/4. So when I multiply those together, 1 times 1 times 1 times 1 is 1, and 4 to the 4th is 256. So the chance is 1 in 256. Now, oh, is it only 3? I'm sorry. I don't know why I did 4. How about 4 to the 3rd? It's 64, I think. Okay, thanks. 1 out of 64. Now, if we had to write that all out, there are 52 cards. So we would have to do 52 options for the first card and 52 options for the second and 52 options for the third. That's a huge number. We don't want to do that. So we rely on this idea of independent and dependent. Now we play the game again. But this time, we don't put cards back in the deck. So what is the chance that the first card is a heart? 13 out of 52, which is 1/4. And we don't put it back. When we make the second draw, what's the chance that it's a heart? 12 out of 51. What if the first card's not a heart? Then you lose, right? And we don't count losing, we only count winning. So we don't have to worry about losing. If we lose, then we're out and we don't get to play. So we only are concerned about what happens when we win. So the next time, we're going to multiply that by 12 out of 51. And the next one is going to be 11 out of 50. So on top, 12 times 11. And then on bottom, 4 times 51 times 50. So 132 divided by 10200. And the decimal is about 1%. The fraction would be 11 out of 858. Is that a lot easier? Does that make sense? Okay. I'm not sure we want to do conditional probability. So conditional probability starts happening in example 6. A given B. So we don't want to do 21 or 22 yet. Okay, let's just go. Man, I don't know. Some of them we can do, but some of them we can't. Example 3, example 4, example 5. Go to 20. And then I'm going to be gone tomorrow.